Filter responses. We have a Butterworth filter. We have Chebyshev filter. We have a elliptic filter. We have Bessel filter. Different types of filters are there. We are not going to discuss all these filters. In our discussion, only we have a Butterworth filter. But one should know there are many different types of filters, because when you start studying in 6th semester, different names will come. Chebyshev filter, different names will come. But you should know, other than this Butterworth filter, there are many different filters are available. But in our linear integrated circuit subject, we are going to discuss only one filter, that is a Butterworth filter. Copied on this, you have a few seconds. Chebyshev, elliptic. Here you can note down one word, flat pass band. Pass band ripples are there. And pass band, stop band, ripples will be there. So these are another one or two words you can remember. But at least different filters are there. One filter we are going to study. That you should know at least. Now, most commonly used filters. You have low pass filters, high pass filter, band pass filter, band elimination filter, all pass filter. I think for your syllabus, I think now they have kept only low pass and high pass. But if a time permits, we'll spend 1 or 2 minutes on a band pass and band reject. Otherwise, we'll discuss in detail a low pass filter and a high pass filter. So just note down the name of the filters so that we can continue. You have a 30 seconds, 40 seconds. Most commonly used filters are a low pass, high pass, band pass and band elimination. And these are the frequency responses you might have studied. For the low pass, it will pass the lower frequency and it will attenuate the higher frequency. High pass filter, it will attenuate the lower frequency, it will pass the high frequency. Band pass, it will pass the set of frequencies. And band reject or band stop filter, it will reject a part of a frequency. Beginning of this also it is allowing, after this particular frequency also it is allowing. So you just copy down the frequency response of filters. It takes a very less time. You can take 10 to 15 seconds to copy down low pass, high pass, band elimination or band stop filter. Take another few seconds, another 10 seconds, do it. Let me wait for you people to copy down. Another 4 seconds, then I'll go to the next slide. Operation amplifier I have discussed. Let me see at least how many of you will answer. The difference between the non-inverting and inverting terminal input is how much? Voltage difference between the inverting and non-inverting when you are doing any derivation, what we consider, and input current flowing through the op-amp, what we consider. So these two you can type in the chat box. You can take a 30 seconds and type a answer in the chat box. The difference between the non-inverting and inverting input is how much? And the current flowing into the op-amp is how much? Be interactive, otherwise I can go very fast and whole portion will be completed within a less time, which is dangerous for you people. So it's better to, I think, interact, tell even though answers are wrong, no problem. Many students are typing. Sumati Gowda, Shreya, thank you. VID, VID should be assuming how much? By ID, Pavan is telling something. So here, the input current entering into the op-amp is equal to, and VID should be how much? All of you are saying VID is correct. VID difference should be how much? I think Naina, Pooja, Sita, Usha, Omkar. Many students are giving the answer. It is a 0. So nobody is typing 2 answers at a time. That is a difference. Somebody should learn that. Do you know education means what? Omkar. Okay. Both the answers, if you could have typed. Somebody has typed VID equal to 0. Abhinandan Appannavar has typed. Like that. At 2 at a time you could have typed answers. So let me go to the next slide. The same thing what you had told. All active filters we shall study are based on the operational amplifier, whatever we discuss in this particular subject. Analysis of a linear op-amp circuit is usually based on the two assumptions. What are those assumptions? Just now we have discussed the difference between the non-inverting and inverting terminal is 0. The current entering into the op-amp is equal to 0. Copy down these 2 points, then we will continue our discussion. The two assumptions, the voltage between the inverting and non-inverting will be difference is VID is 0. Current entering into the op-amp is 0. We have discussed already, but in this chapter as a prerequisite he has mentioned. That's why we are discussing this, so that again you should not ask, sir, you didn't consider the current flowing into the op-amp during the derivation. That point should not come. Okay, let me go to the next. Okay, this video is already available in the YouTube, and this is a part 2. 3 part I have made, I think. It is the second part. The same slides I am using here also. Some additional slides I may be using in the class because we update always. Capacitor with the blocks AC or DC. You can type the answer. Thank you, Abhinandan. Thank you, Shreya, Pavan Gutti, Anusha, Paschapur, Ulvesh. Very good. Sita. It blocks DC. See, I think Sriranga, Parvati, Shivam, Diksha, Divya, all are saying it is a DC. It blocks DC. And at higher frequency, capacitor acts like what? Second answer. Umakant, Vishal, Kirtis, Sugnani, Patil. Oh, I saw a name now. New name. Akshay, Rajat, Ulvesh. Conductor. Okay. At high frequency it acts as a Ulvesh is giving a very nice answer. Shreya Umarani and Vishal. Shreya. Oh, one more Shreya is a Padukoni. Jnanashri. Short circuit. Conductor. All answers are correct. This was asked by some teacher in some Viva question. Some student has answered. How? Why it blocks DC? And why allows AC? Why the AC current will flow through the capacitor? And why the DC will be blocked? The student has answered so nicely. Not our student. Our students are very good. And he explained so nicely. Sir, it's very simple. DC is a straight line. It's coming like this and it will be blocked. But AC is coming like this and it passes. So this is the way how the student explained to the teacher in the Viva. And I'm sure our students are not going to explain like this. They explained so nicely why it blocks DC and why it allows AC. And all of you know the equations, everything we have discussed in detail already. Let me go back to the next slide. A low pass filter, and this is I'm giving a higher frequency also as well as lower frequency also. Low pass filter will pass the lower frequency, whereas higher frequencies are attenuated or not at all passed. This is a response lower or pass band. This is a stop band. A small circuit. Understand this. Nothing is there in this. Just now I have told. Low frequencies will be passed because it blocks the DC. All lower frequency will go. As the frequency increases, automatically those will be grounded. Those will never be passed. I take a 1 minute and copy down this. It's very simple how the low pass filter RC combination works. So with amplifier we will see later. Just I wanted to convey you how the low pass this RC combination acts as a low pass. And if you interchange now this capacitor, this as a resistor, it blocks DC or lower frequency. Later it becomes conductor, higher frequency. Therefore it is a high pass filter if I interchange these two positions. Once if you know RC combination, why it is high pass, why it is low pass, a fundamental, then followed by amplifier will be there. Nothing else in the filter. This is the only basic one should understand Copy down and try to understand. A low pass filter is a filter which passes a low frequency signal and blocks or impedes high frequency signals. All the images I am using so that I believe a picture tells 1,000 words. Instead of orally explaining all these things, higher frequency, this definitely acts as a conductor. Those will be grounded, you won't get. Hence, only low frequency you will get as output for one RC combination. If I reverse the position of these two, automatically it becomes a high pass. Lower frequency will be blocked here only because of C. If I interchange, I am talking. So I'll wait for another 10 seconds, then we'll go to the next. Okay, let us go to the next. Order of the filter. Order of the filter means the maximum number of delay elements used in the filter. So one capacitor, if I am using, it's the first order. Two capacitors if I am using, it's the second order. If I use 3 capacitor, I'll be definitely it's a third order filter. So this is one point which you have to remember. And first order 20 dB per decade will get roll off, or in terms of octave if you want 6 dB per octave. And second order 40 dB, third order 60 dB, fourth order will get 80 dB per decade. Decade means all of you know in the semi-log graph. Or octave means up to 8, it is up to 10. So this you might have plotted in your third semester also. And the same point I am discussing. And how is the order of the filter matter in the graph when you plot in the semi-log graph this response? So if it is a first order, it is a 20 dB per decade. Second order, it is a 40 dB per decade. Third order, it is a 60 dB per decade. So like that, etc. 4, 5, 6 he has mentioned. This is a basic things one should know. All are given in one slide as a summary. Go through whatever you want, you copy down from this particular slide. Order of the filter depends on the C, how many you are using. First order, I use only C. Second order, C1, C2. Third order, I use C1, C2 and C3. First order is a 20 dB, second order is a 40 dB, third order is a 60 dB, like that it will go. And this is the way how it changes. First order, second order, third order, fourth order. Ideally it is like this. You won't get ideal, which is very difficult. But we are, as order of a filter increases, it is going towards the ideal. That is the one point which you have to remember. Let us go to the next. Copy down. Don't need to copy down these frequencies and all, and dBs also. Just note down this as a frequency, this as a gain in dB. That's all. No need to. Anyway, you are going to conduct the experiment later. If this lockdown is it removed, or even you can do the simulation also in your home only. Okay, we are going to discuss the first order low pass Butterworth filter. Before this, let me spend 2-3 minutes to discuss some other things. Answer these questions even though it is out of syllabus, but it is a must. You should know what is the meaning of education, purpose of education. You can answer. We will spend 2-3 minutes on this. Thank you for all your answers. Most of the students, they have typed their answers. Rajat, Shreya, Pooja, all of you have typed your answer for that question what I asked. Thank you. And this motivates you people to type again. When somebody does something good, you should motivate, encourage. Even though that may not be a great thing what he or she has done, automatically it helps him to do better again. So let us go to the next slide. Humanity is dangerous for the society also. Okay, so let me go to the next. And now, low pass filter. This is a first order low pass Butterworth filter. Why the name is Butterworth? It is suggested by that person. He has kept his name. So copy down this circuit and this response, and you have 1 minute time. The first order low pass filter. Hope most of you have copied this now. Let me go to the next. This is the R and C combination first order, and I'm giving it to the non-inverting. Can you type non-inverting means gain is given by equation in terms of resistors, all of you know. Can you type the answer in the chat box? Gain of the non-inverting amplifier is given by, maybe using somebody laptop or somebody maybe mobile, but you people can type. Thank you. Ritin, Gaonkar, Pavan, Preeti, Abhinandan, Shreya, all are typing 1 plus RF by R1. Vinay Kumar wanted to type complete, but one after that he has entered key. Manjunath, Pooja, Rakshita, Sita, Shreya, Rakshita, all are typing 1 plus RF by R1. Very good. Siddhartha, Sahana, Sriranga, Rajat, Vinayak, Wali, all are typing the answers. Very good. Thank you, Ritin Gaonkar, Pavan, Amog, Nischal. And we are using a R1 and RF. Sriharsha, Muttu, Ashish Kulkarni, Amog Kulkarni, Nischal, Divya, Umakant, Usha. Correct. 1 plus RF by R1 because you have taken R1 and RF. And hope all of you completed. Let me go to the next. See the derivation we are going to do for a gain and write a voltage across the C. So all of us know in network analysis you have done all these things. Minus JXC divided by R minus JXC into whatever the input I am applying V. This is the equation what I am writing. Hope all of you can understand step by step. Don't copy down. I will give the time also. First you understand what I am explaining. V1 I want to write. So I have a JXC and impedance. Here total becomes R minus JXC. Input is V. That is the equation what I have written. And all of us know in already have studied. J is nothing but square root of minus 1 and minus JXC is nothing but 1 by 2 pi FC. This you have studied already. And filling these two, whatever JXC value in this equation. So I am rewriting, that's all. Minus JXC I am writing as it is, and R minus JXC is there. R I am writing as it is. JXC I am filling this value. Again into Vn is there. So that Vn I am keeping as it is. Try to understand. The steps are very simple. Now I am rewriting. That's all. Now what I will do? I will take a LCM J2 pi FC. This will come into the numerator, and simply denominator I will get J2 pi FC into R plus 1 into J2 pi FC. So this is what I am going to get. And now this is what I am talking. It is a V1 only. Voltage across the capacitor I am talking. This is one important point you have to remember. And copied on this. Then I will discuss next. Take a minute and copy down 3 lines. Try to write an equation V0 equal to gain. All of you already typed. I want V0 equation. It may be wrong also, no problem. Try to write the equation. I'll be happy to see your name and read your name in the chat box. You may do wrong in the beginning, no problem. But we have discussed already many times. Now V0 equal to, I have to write down the equation. Try, it may be wrong also. Just type your answer in the chat box. Okay, thank you. Gain into V1, Vinayak, Damodar, very good. Naina, 1 plus RF by R1 into V1, sir. Yeah, it is correct. Yeah. Ganashri, it is not a V in. Thank you for writing the answer. But remember, I am giving a input is a V1 here. Observe carefully. Whatever the input I am giving to the non-inverting terminal, that will be amplified by how much? 1 plus RF by R1. This we have discussed many times. Why I am repeating the same question to you people? because you should remember what we have discussed, so that whenever you are designing anything, it will become easy for you people. So always remember gain into whatever I am giving the input to the non-inverting terminal. That time nothing was there here. Directly I was applying V in here only. When I directly apply V in here, automatically 1 plus Rf by R1 into V in we used to take. But now I am not applying directly. So here the voltage whatever is there at non-inverting terminal, that should be taken then into gain whatever is there. And the same thing I am going to show you people now in the next slide. What I am doing, so 1 plus Rf by R1, now Ashish has typed, Divya, Siddhartha, Sriharsha, Umakant, many people are typing 1 plus Rf by R1 into V1. Now V1 I will fill as it is from the previous slide. Vin divided by J2 pi FCR plus 1 I will fill it, and then I will continue. Now I am rewriting V naught equal to AF divided by 1 plus J F by FH into Vn. Vn I am keeping as it is, and AF equal to 1 plus Rf by R1, that's why I am writing AF. Then AF and Vn is over. This I am writing 1 plus F by Fs into J. What is the F equal to? Frequency of the input signal. Fh is 1 by 2 pi RC, so that it will become 2 pi FCR. So just take 1 minute and copy down these two lines. The slide. So for the first order low pass Butterworth filter, the gain, magnitude and phase angle equations in polar form are given like this. V naught by Vn equal to F by square root of 1 plus F by Fh square we take, and phi equal to minus tan inverse of F by Fh. So phi is a phase angle in degrees. Note down these two. And sometimes they may ask you to write in the exam. Copy down these two equations. At very low frequency, F is very less than Fh. F is less than Fh. This term will become small, and 1 plus this doesn't affect AF. When both are same F and Fh, it will become 1, and 1 square plus 1, 2, AF by root 2. When this F is very high, so this become a number, so automatically it will AF divided by some number will get total. So that's why it's less than AF. Similarly, we have to discuss a second order low pass Butterworth filter, first order high pass Butterworth filter, second order high pass Butterworth filter. The gain equation you have to remember, and you have to only for first order derivation is there, but second order directly you have to remember the equation. Okay, hope most of you have completed, and let me go to the next. Yeah, this is the same thing what we have discussed. Low pass filter has a constant gain AF from 0 Hz to FH Hz. At FH it will become 0.707 AF. We have discussed just now. After FH it will start decreasing. Y also we have discussed. And the gain decrease will be how much? It's a 20 dB per decade because it is the first order. Frequency FH is called as cutoff frequency. Just copy down 1 or 2 points from this slide. I will wait. How we are going to design, sir, low pass filter? Choose a value of a high cutoff frequency, how much you want. Select a C less than or equal to 1 microfarad. Calculate the R. Why you have to select the C? Can we select the R and can we calculate C? Okay, so lot of discussion we had why one should not select R and calculate C. You have answered. Now copy down these steps and try to understand. Thank you all of you. Take care, be safe.